Hello, my name is Aidan Collins, and today is October 23rd, 2025, and this is my UNE Online Chem 1020 video explanation for structure elucidation problem-solving process. For this assignment, I was given the molecular formula C10H12O, and the first thing that I did was I calculated the degrees of unsaturation. For the formula for that is 2 times the number of carbons plus 2 minus the number of hydrogens in the molecular formula over 2. So that came out to 5. And what that tells us is that we will have 5 pi bonds in the final structure. And knowing that there's 5 pi bonds, it hints us towards either um, a ring of some sort, and a lot of chemical shift, and a lot of anisotropy and polarity between the carbons in that ring and the functional groups attached to it. So the next thing after calculating the degrees of unsaturation was to look at the IR spectra that was given towards us, or given to us. What we can see from that is that there are three main distinct functional groups. We have the two types of carbon CH bonds. We have sp2, sp3 here in the 3000 range. And then we have the double bond area, which we have a huge spike here at 2700, or sorry, 1700. At 1700, sorry, look at my notes. At 1700, we have the C double bond O, and then right next to that, there's a second spike, if you can see there pretty clearly. There's a C double bond C, and then in the 2000 to 3000, or in the 1400s, we have all the sp2 carbon-carbon bonds that signify the benzene ring. Um, so there's three main distinct groups. We have the CH bonds, sp2, sp3, sp2 being above 3000, sp3 being below 3000, and then the double bond region, and then the benzene ring region. After that, we have the carbon-13 spectra, where we also have three distinct functional groups, but more spikes that go along with that. So starting all the way down at 200, right below 200 is the aldehyde functional group that comes off of either benzene carbon 1 or carbon 4 on the benzene ring. The carbon that is at 192 is the carbonyl carbon that has a double bond to the oxygen. And then next to that at 157 is the benzene benzene carbon that is attached to the aldehyde group. The reason that that is found at 157 and not lower or more upfield, closer to 0, is because of the amount of anisotropy caused by the double bonds, and the shielding and deshielding causes a huge chemical shift for that carbon, and its attachment to the functional group, all the shifting of the double bonds within the benzene ring. And then next is the three spikes in the 150 region, which are all, or sorry, the 128 to 135 region, which are all the carbons for the benzene ring. Because there is symmetry in this molecular structure, and constant resonance within the benzene ring, that has caused a lot of chemical shift and anisotropy, and so that's why that is found in the 130 region. Next, further down is similar to the IR spectra. We have the sp2, sp3 carbons, and the one right here, the shorter one, is the sp3 carbon that sorry, I can't read backwards. Is the sp3 carbon that is at the center of the isopropyl group, which is the other group that is coming off the benzene ring. So the isopropyl, this central carbon there, which has bonded 3 other carbons and a single hydrogen. It has a smaller it shows up as a smaller spike on the spectra because it is um, has more shielding. And then, or I mean, less shielding. And then the taller spike is the 2 methyl groups that are coming off of that carbon for the isopropyl functional group. The final graph that we have is the proton spectra, and this one is a little bit easier to read because we have less protons to count. Starting at 0 or further upfield is the biggest spike, which is again the 2 methyl groups. So very similar to the other structures, we can see that there's the 2 methyl groups which cause a huge spike. They have an integration of 6H because they're right next to a bunch of hydrogens. So these are all the protons for the methyl group. And then this little tiny septuplet multiplicity hydrogen is just like the last, the carbon-13 spectra. We have a tall spike next to a smaller spike, that being the hydrogen attached to that sp3 carbon CH right there. So then going further downfield, we have very similar to, we have the benzene ring, which has the 2 protons coming off of those aromatic carbons, and the reason there's only 2 spikes, and there's 2 spikes, and then each one's a doublet because they're only right next to each other. We don't count the other ones coming off of the other side of the benzene ring because of the symmetry, the line of symmetry for this structure. So only counting those 2 protons off on the benzene ring. And then the final proton counted is the one on the aldehyde group, H1 integration, singlet, multiplicity. These are doublets. This is septet and the septet, and then this is also a doublet right here. The big spike on the on the on the methyl groups. All right, final sheet for the assignment is the charts that I filled out while looking at the graphs. So starting from the IR spectra, we have we'll start all the way downfield, and we'll start with the benzene ring. We have all the carbon-carbon single bonds, sp2 carbons within the benzene ring. Those technically show up further downfield, but these carbon-carbon single bonds in the benzene ring, the way that they show up on the spectra is in the 1400s. So that's where the benzene ring is, and then right above that is the carbon-carbon double bond that is also within the benzene ring. That's at 1600. Right in the double bond region below the carbon oxygen double bond. So we have the single bonds in the benzene ring, the double bonds in the benzene ring, and then we have the single one on the aldehyde functional group before getting to the sp2 sp3 carbon hydrogen bonds that are further upfield, sp2 being above 3000, sp3 being below 3000. Next is the carbon-13 graph, which we can again start. Let's see what that starts at 192. So we're going to start all the way downfield at 192 with the aldehyde group. We're measuring the carbon, that is the carbonyl carbon, double bonded to the oxygen and single bonded to the hydrogen. And then next down is the aromatic benzene ring carbon that is attached to the carbonyl carbon functional group on either, we can consider it carbon 1 or carbon 4. And then again, that's found so high up because of the anisotropy and polarity and caused by the de-shielding and shielding, the constant resonance of the double bonds within the benzene ring, so that causes a huge chemical shift um, in that carbon or in that carbon 1 or carbon 4, whichever you want to call it, based on the resonance. And then we have three inputs here for the benzene ring carbons. We can either count them. I didn't underline because you can either count it as the single the sp2 carbon that is attached to the hydrogen, or you can call it also the sp2 carbon that is attached to double bonded to the other carbon. So you can read those as either the carbons in the benzene ring, depending on the resonance at the time. And then all the way down is the sp3 carbon for the CH, sp3 carbon for the um, right here underlined for the isopropyl group, before the two methyl groups, the two sp3 carbons for the methyl groups um, coming off of the benzene ring. Yeah, and then the last one the is the uh, proton spectra. So we have, this is a little bit harder for me to read. We have, starting at 1.3, we have the two methyls coming off. They have a integration of 6 because they are adjacent to each other, and the hydrogen or um, and the hydrogen on the CH that connects the two methyl groups. Um, so they have an integration of 6, and then the multiplicity of doublet because they are only counting one of each other, uh, and then oh yeah, they're only counting one of each other, and then the hydrogen um, on the CH, and not counting the other three, hydrogens on the other methyl group because of the symmetry. You only count one of the methyl groups, so it'll only be a doublet. But that being said, then this carbon here with the CH will have a septet because it's attached to two methyl groups. So that's a little bit interesting, a little bit funny to deal with, but that's how that works out with the degree of symmetry. And then going to the benzene ring right here, we have two protons coming off of that. So we have two inputs there, both doublet because they're only right next to each other. Um, and then they have an integration of 2 as well. N plus 2 is, or N plus 1 gives itself 1. So we are at doublet, and that's at in between 7.4, 7.8. That's where they show up. And then finally, the proton on aldehyde group, the lone proton, the singlet, the H1 integration, this lone guy over here coming out at 10, because and telling us that that's an aldehyde group. Through most of this, I was confused looking at the other graphs. Um, looking at I saw that we have a carbon oxygen single bond, and then again here we have a carbon oxygen double bond, and I wasn't sure if that was going to be a ketone group or an aldehyde group through most of it, but then I got to the end and I looked at the hydrogen spectra, and that is what told me that that was going to be an aldehyde group. That's what told me that there was a proton there and not a ketone group. So that led me to the final structure, which is a 1,4-isopropyl benzyl aldehyde, which you can see it's a di-substituted, para-di-substituted benzene ring with two functional groups coming off of it. Um, and yeah, that is it. Thank you very much.